Assalamualaikum, sir.
Assalamualaikum, walaikum salam. Uh, I hope three students who are left are going to come quickly. Okay, so let's start. And I have shared my screen presentation.
So before start, kindly let us know that whether the final paper date is confirmed or not, whether it will be on 12th or later on.
Up till now, it's still 12, and the news is that it would be on site. That is, the exams would be held at NED University campus,
Okay.
main campus, right? So no formal letter has been received from the examination department yet, but this is the news that the exams would be held on site, and the schedule that has been shared with you people on your group, that's the latest one, right? So according to that schedule, we are going to have exam on 12th October.
Sir, is there any possibility to extend this date?
uh, I don't think so, not at this point of time, not at this point of time. Uh, it's I think so. uh, yeah, that has been decided. What I was talking about, that 12th is the date for the examination, and it won't be extended. I am not sure, because
Okay, sir. Okay,
we had
sir.
started the semester also late, and because they had a problem to start new semester in this whole year, and they are going to plan for that as well. So they have already announced the interviews for the next semesters for new batch intake. So I don't think so it would be extended, and that's why they are not giving it even a week gap in between the classes and the exams. So that's another thing, because normally the master students always used to have 1 or 2 week gap between the classes and the exam,
Yes,
right?
sir. That's what I
So
want. At least if we get 1 week gap, it will be more appropriate.
uh,
So
I
on the
know,
other way,
yeah, I know.
can
And
you
from the students'
can you
perspective,
squeeze
this
your
is
lecture? Can you squeeze your lecture? Make it this lecture as the last lecture. Will be grateful to you, sir, if you can,
no, that won't be possible as well.
because the
But
course is too lengthy to cover.
yeah, but I'll try to do one thing, that I'll give only those lectures starting from lecture number 9, um, because from lecture number 1 to 8 we had covered that in the midterm, so that becomes 9 to 15. So that would be 7 lectures, and they would be part of the final exam. So previously I used to give from the whole course, but now I'm going to just concentrate on the last 7 lectures in the
Thank you, sir.
final exam. Okay.
Thank you, sir.
Right. So let's start.
So one thing
So
more. What about the midterm?
I have
Because
checked
the
a
midterm is
few of
not too
them.
much.
Yeah, I have checked a few of them, but I'm going to check that by tomorrow, or the remaining one by tomorrow or sometime. But the few that I have checked are not very good. So people have done just 3 or 4 questions. I was expecting at least more than that. But those who have attempted it are also not very sure about what they are writing, and what should be the right answer. Even though that was an open book exam, the Booth algorithm was wrong, the division algorithm is wrong. So these are things that you have to look at, because that was an open book exam. So in open book, normally people don't make these kind of mistakes. Anyhow, I'll give you the final result in the next lecture. That would be our last lecture, inshallah. Next that would be next Thursday. Okay. Right. So yeah, we were discussing about, in lecture number 13, we were discussing about compiler techniques for exposing ILB. Here we discussed about loop unrolling and pipeline scheduling, right? So how can compilers expose more of instructional parallelism? How can the compilers fill in those stall cycles, those gaps left because of control hazards or data hazards. So the compiler can reschedule the program on its own, looking for instructions which are independent. And then this is what we studied in the last lecture regarding compiler techniques for exposing instruction level parallelism. Then we discussed about static scheduling. That's the same topic. Actually, static scheduling is done at compile time, so that's covered under the compiler techniques. Uh, then we looked at dynamic scheduling. So this is something which does not need an efficient compiler, but here we need some extra hardware to support our scheduling technique. We call that dynamic because this is done at runtime. So at that point of time, the instructions are going to be executed, the instructions are going to be fetched, and whenever you see an instruction that can go to the execution stage, you are going to go through that. So you're going to let that instruction complete and before the previous one. So we looked at a Tomasolis algorithm. Here we talked about reservation stations along with the functional units. So let's suppose we have add functional unit and multiplication functional unit. Along with those, there were reservation stations, and each reservation station entry has its own name. So here we do register renaming at the hardware level by replacing that register name with the reservation station number, reservation station's name, right? So whenever you want to get some data from a particular register, so instead of that register name, you're going to provide that reservation station numbers, reservation station entries name. And this is how if you're talking about running that instruction in a loop, even where many instructions are writing to the same output or going and reading from the same register, you are going to see that they are not actually going to get it from that same register, but they are talking about the reservation station name. So this is how register renaming is done at hardware level. And we saw that there are three stages mainly: the issue stage, the execute stage, and the write result stage. And in our last example, we looked at what is the starting cycle for a small code that we were looking at, and what is the time or the cycle when these instructions executed, they completed their execution, and what was the time when they completed their writing. So we are going to talk about that, but the main thing here is about exceptions. Now, as we have discussed earlier as well, exceptions are the interrupts. They could be software interrupts, they could be hardware interrupts, but they could be internal interrupts as well, and they are called as exception. So we call an exception as imprecise if the processor state when the instruction exception is raised does not look exactly as if the instruction were executed sequentially in strict program order. Now, there is a strict program order where you have one instruction running at one time, right? Then if you change that order and try to run an instruction earlier than its stated order, then what would be the state of the exception whenever that exception is going to occur? So I'm going to explain that through let's talk about a few instructions. So let's say we have an add instruction, and we have a multiplication instruction, right? And let's say we have a subtract instruction. Okay, so this multiplication instruction is dependent on add, but this subtract is not dependent on multiplication or add, right? So when you're going to issue them, they are going to be issued in this order. That is, add would be issued first, multiplication would be issued second, and subtract would be issued third, right? So let's say what happened was that add is doing its work, and one of the operand is, for example, dependent, and add is also dependent on some other instruction, and maybe this is also pending for its result. So add is not going to go through because one of its operand is not available. Then since multiplication is depending on add's result, so multiplication cannot also go through, but subtraction was independent of add and multiply and the instruction that was producing that result as well. So subtraction went through and subtraction started. right? So subtraction started, and at some point of time, the result is available, right? So at some point of time, that result was available, and then subtraction completed its task. So subtraction was about subtracting R2 and R3's value and storing that in R1. So this completed the task earlier than addition and multiplication, and so it's going to write its result in R1, right? Now this is our scenario here. Um, Now let's say there can be two things that are possible now. What if whenever that previous instruction, previous to add instruction completed its result, or you can say during its operation, this instruction generated an interrupt or an exception which needs to be handled, right? So during its, so maybe let's say this was a divide instruction, and during the divide operation, there were some problems, because we know division operation has got some issues, like you cannot divide by zero. So if one of the denominator is zero, then obviously this is going to create an exception. Now sometimes it happens that divide also can result in overflows, that we saw earlier, that the quotient cannot come in the required number of bits. So that is also an exception, right? So there can be different exceptions in divide. So let's say this divide instruction generated an exception. Now what happens when you have an exception is that you normally store the state of the processor at that point of time, and then you continue from the next instruction. This is the case when you are going to deal with exceptions, that whenever an exception is going to come, you're going to store the state. You're going to jump to the exception handler. So that's another program written somewhere else in the memory, right? And sometimes also called an interrupt service routine, an ISR as well. So what happens is you're going to jump to that particular program, execute that program, and then come back and resume from the same place. Now let's talk about two scenarios here. Now let's talk about how you are going to do that in a normal processor. So a normal processor is going to deal with these instructions one at a time. So if the division is not going to complete, then add, multiply, subtract are all going to be waiting, and they cannot do it their task, right? So this is the normal case, which we have mentioned over here as in this slide as if the instruction were executed sequentially. So this is the sequential way that all of them are going to do their task one after another. So this in a sequential way, all of them are going to do their tasks one after another. But when you're talking about dynamic scheduling, what's going to happen is division hasn't completed this task, and subtraction has completed this task, and add and multiplication haven't started yet their execution process as well. So if an exception is going to come, and during that service routine, when you're going to jump to that program, where are you going to come back? Are you going to come back to this place where you're going to start addition, multiplication, and subtraction again? Now for addition and multiplication, it's okay, because you didn't do any work for that. So they are going to execute the first time whenever they are going to come back from the exception. But what about subtract? Because subtract has already completed the task and already stored the result in R1. So you are going to again subtract the values of R2 and R3 and store that in R1. Now this might not be a problem if you do that again, because you are still going to subtract the value of R2 and R3 and put that in R1. But what about instead of this R2, if I had something like R1 over here? So if I was trying to subtract R1 with R3 and putting the result in R1, now if I redo this instruction once more, then this value was already stored earlier, and I'm going to use that value and I'm going to subtract it again from R3 and put that again in R1 if I redo this subtract instruction again after the exception has been handled. Now this is one case where exception is generated by an instruction which is earlier in program order, right? And we have completed an instruction which is later in program order, right? So this is one case. The second case is that again, assuming that division is has not completed the task, add and multiplication are still waiting, subtraction has completed, has started its execution, right? And during its execution, the exception was not generated by division, rather it was generated by subtract instruction. So during its execution, subtract also can generate an exception, because sometime it might happen that there is an overflow over here as well in subtract. So if subtract generated an exception, so this means you have to resolve that through some other service routine, and then you're going to then come back. So where are you going to come back? Because normally we come back to the next instruction, right? So if you're going to come back over here, then we are going to see that these three instructions, maybe divide has already started but these two, add and multiply, haven't started their execution, so they are not going to complete it. They are not going to complete, and so this means that the program result would be different than what sequentially executing program would have generated, right? So these are two cases. So one of the cases that an instruction early in program order generates an exception, and one of the instruction later in program order has already completed. So do we need to redo that instruction? The other case is that the later instruction has generated generated an exception, and earlier program instructions haven't completed yet. So where are we going to resume? So these are different conditions which are going to make exceptions imprecise from the sequential executed program, right? And we need to look at this point of how to make how to make exceptions precise. These are two possibilities that I've just discussed. The pipeline may have already completed instructions that are later in program order than the instruction causing the exception. This was the case when if you're talking about the first one here. So what we are saying here in this first one is the pipeline may have already completed instructions that are later in program order than the instruction causing the exception. This is the first case that we saw over here. That is the subtract instruction has already completed, but the previous one has generated an exception, right? The second one is the pipeline may not have yet completed some instructions that are early in program order than the instruction causing the exception, right? So this is the second case where we see here that an instruction is generating an exception, but the previous to that instruction haven't completed yet, right? So these two possibilities are going to make the exceptions imprecise. So when you make the exception imprecise, this means that this program's behavior would be different than how it would have run on a sequentially executing processor. Now, from a programmer's point of view, the programmer thinks that the instructions are going to run in sequential order. But we are doing out of order execution to make things fast, right? But we should also ensure that these exceptions, if they come, are also handled in the same way as handled by a sequentially executing processor, right? So how to make these exceptions precise? Now, both Tomosolo's and the scoreboard algorithm do in order issue, that is, instructions are fetched in order. Out of order execution, that is, they can execute instruction out of order. And out of order completion, that is, these instructions are allowed to complete also. And completion means that they are allowed to write their results in the respective registers also out of order. Now, this last part, out of order completion, is something which we need to fix. Why? Because if we need to redo something, if we need to redo an instruction and it has already stored its result, then it would be very hard to take that result out and make it from to the same state as was there in a sequential executing processor. So that's going to be a little different thing. So from our last example, we saw that issue is in order, which is okay. Execution is out of order, which is also okay, because we can do execution out of order. That is what makes our program faster. This is the last step, write result. Now, write result is out of order. We need to make this in order. Now this is the only thing that we have to change to make instructions exceptions precise. So in order to make exception precise, we should ensure that writing of result means that writing to these registers, right? So writing to these registers should also be in order. In order means that these instructions, whatever their order is, the result should also be written in that same order. So for example, if multiply is going to complete in 15, it's going to write its result in 16th cycle, then any instruction later than multiplication is going to write its result after multiplication, because that's the program order. So we can see here subtraction has completed result in 7. So what we are trying to do is we need to save this result, but we are not going to write it to F8 yet. We are going to write it to F8 when multiplication has written the result, because we need to have this right result also in order. So after 16, in the 17th cycle, we are going to write the result of subtract. Now, if we write the result in order, this is going to ensure that the exceptions are always going to be precise. Now, this same technique is implemented in all the latest processors. We call this as hardware-based speculation. Speculation means to speculate or to predict which instruction, to guess which instruction would be the next instruction, and try to execute that, right? Because if you are thinking about branches in the program, this is a very good technique, because for branches we don't know which instruction is going to be our next instruction. So what we do is we speculate, or we think that this is going to be our next instruction, and we execute it. The only thing problem here is to write the result back to the register. We are going to delay that process. We are going to stop writing. We are going to have some kind of a structure which is going to store that result temporarily in another place. It's not going to write to that register, but it's going to store that internally. And then we are going to make that right step, that last step, which is to write the result in order. Now, if you make that in order, everything is going to go fine. So all the exceptions are going to be okay. So you just need a little modification in a Tomasulo's algorithm. So Tomasulo's algorithm is not exactly implemented in the same way in recent processors, but we just try to change that in a different way. So we are going to see about that. So that technique is also part of dynamic scheduling, and it's called as hardware-based speculation, right? So what we do here is, as I've discussed, we are going to separate execution from completion, right? So execution can be out of order, but completion should be in order. And in order to do that, we have introduced another stage, which we are going to call as instruction commit. So instruction commit means that whenever that instruction is going to write its result to a register or a memory location, so that last step should always be in order. So commits are always going to be in order. And for that, what we need is a special hardware that is going to store the result till that instruction's turn comes, till that instruction which has already executed its result. So that result will be stored in a special structure, and we are going to hold that till that instruction's turn comes for commit, right? So we are going to ensure that commits are always in order. So that structure is called as a reorder buffer. So remember from our last lecture, whatever we had studied, we are just going to include one thing more in that whole thing, and that is called as a reorder buffer. So there are some changes from our last lecture, but the main thing here is this is a special buffer which is going to hold the results. And since we are talking about storing the results in reorder buffer, now instead of reservation station names, we are going to rename the registers by reorder buffer entries, not by register reservation station names, right? So I'm going to come to the example shortly. So the whole idea is that we are going to have a structure like a reorder buffer over here, which is a small memory, and it's going to hold the results. Along with that, there are going to be different other entries which are going to hold the status and the reservation station name also over here. And this is connected to the floating point registers. So normally what was happening in our last scheme was whenever the result is going to be broadcast, it's going to go to all the reservation stations and also updated in the register. But what we have done over here is we have introduced a reorder buffer along with the floating point registers. So reorder buffers are going to ensure that the instruction whose turn is for commit only writes to the register or memory location. So memory location is not shown over here, but again, memory locations are also going to go through the reorder buffer because commit is the last step. Commit means to write to the register or to write to a memory location, right? And you can see over here the reservation stations are not taking the results anymore. So previously reservation stations were waiting for something and then they were getting that results. All those results are also going to come from the reorder buffer entries, right? So I'm going to come to that. I'm going to just write down the main points over here. So the reorder buffer is going to hold instructions in first in first out order, exactly as the program order. Uh, Instead of reservation station name, now we are going to reference everything by reorder buffer entries. Whenever in a reservation station we were talking about operands not available, and instead of that those operands we were writing the reservation station names, here we are going to just reference them by reorder buffer entries. Whenever an operand is not available, we are going to just talk about where in the reorder buffer entry are we going to get that operand from, right? And once an instruction is going to commit, whenever it's the turn of that instruction comes, and that turn is going to come in sequential order in the same program order, then result is going to be stored in the register, right? So I'm going to come into an example. So it's a very simple structure. It's a first in first out buffer. So you know how a first in first out works. There is a head and tail, and you can just add to the tail and get that this head is the instruction which is going to commit. So whenever instruction commits, then you have a new head, and then this entry is free. So and the tail can go and it's something like a wrap thing. So if two entries are filled over here, then it's going to start filling it from this side as well, right? And the head is going to move to the from the left to the right in this diagram, right? And the tail is also going to move from the left to the right? And this is wrapped. What is going to be stored in the reorder buffer? So we are going to again store the instruction type, the state that these two entries were also there in the reservation station, the destination here where the result is to be written. So for example, this is something new. In the reservation station, we were not talking about the destination. Here we are going to talk about where is this result going to be stored, like the register or the memory address. And the values, operands, the results that have been completed. So that's the main point, that whenever you are going to execute something, you are going to get some result. That those results, before they are going to be written in the registers, are going to temporarily hold in the reorder buffer. So they are going to store the value as well. And additionally, they are going to store the reservation station. Additionally, the reservation station field is going to also store the reorder buffer entry number, right? So as we are going to come to an example, this would be much clearer. So now we have got 4 steps instead of 3. So the first 3 are the same: issue, execution, write. We have introduced another one, commit, right? So commit means that we are going to update that register. And the write result, in the previous Thomas's algorithm, in the write result stage, we were actually writing the register. Here in the write result, we are just going to update the reorder buffer entry, right? So we are not going to write to the register. We are just going to update the reorder buffer entry. And whenever that instruction's turn comes, then you are going to write it to the register. So all those things which are written in red are the changes over here. So you can see in the issue step, We were previously only checking for reservation station whether they are free or not. So now we are going to check if reservation station and reorder buffer slots are free, because again reorder buffer also is going to have some fixed entries, and reservation stations are also going to have some fixed entries. So we are going to check first of all whether you can issue a new instruction at this point of time, because if there are many pending instructions, then the processor obviously has to wait. So if the reservation station and the reorder buffer slots are free, then issue the instruction and send the operands and reorder buffer number for destination, right? Execution remains the same because there is nothing here. You can start execution whenever the operands are available. The write result is just going to update the reorder buffer entry. It's not going to write to the register. In the commit, we are going to update the register with the reorder result, right? Okay, so what is going to happen if we execute an instruction which shouldn't be executed? Like for example, in a branch, we don't know whether that branch instruction would be is the right instruction to execute. So we are going to just speculatively fetch an instruction, execute that instruction, and we are going to write the result of that execution in the reorder buffer. Now, if we are wrong in our prediction, so what are we going to do? We are just simply going to remove those entries from the reorder buffer. So this is an easy thing to do because we have not updated the registers yet. So we have just executed them and stored their result in a reorder buffer entry. If we later find out that this instruction shouldn't have executed, then we are simply going to remove those results from the reorder buffer entries. Since they have not committed yet, because a commit is always going to be in program order. If an instruction turn comes for a commit, this means that instruction should execute, right? So speculatively, we are going to issue an instruction, execute an instruction. After the execution is completed, the results are going to be stored in the reorder buffer. But if later we find out that this instruction shouldn't have been executed, then simply we are going to remove those entries from the reorder buffer, right? What happens when an exception is going to come? So again, the two cases that we discussed here, that division, add, multiply, subtract. So division is working, subtract. So what we are going to do over here, I'm going to just redraw this again. So we had divide, which was the first instruction, add, which is waiting on divide, multiply, which is waiting on add, and then subtract, which is not waiting for any one of them. So since divide is a long process and it hasn't completed this task, so and we are assuming that subtract has executed. Now what is the subtract going to do? So if the subtract has to write the result in R1, so what we are going to do in a reorder buffer, we are just going to maintain that subtract is going to write its result. So we are going to compute that result. So let's say that result is 100. So that result is also going to be over here. And we are going to say that it's going to be written in R1, but we are not going to write it yet, right? So we are not going to write it yet. Now, what if an exception comes from the division part, right? So if the divide instruction issued an exception, after servicing that exception, we are going to return to add and then multiply and then subtract. So we are going to redo subtract, but that's not a problem now because we have not changed the value of R1. Even though if we have got an instruction like this, it's not going to be affected because it's going to see the same R1's value which was previously there. So we are not going to update the value. We have stored the result in the reorder buffer. But we hadn't updated R1 yet. So if we redo subtract again, that's not going to be a problem anymore. So exceptions are going to be fine if it's generated by an earlier instruction. That was our first case, right? Our second case was what if an exception is generated by an instruction later in the program order and then there are still pending instructions before that particular instruction. So let's talk about our second case. So what if subtracts generate an exception? What if subtract generates an exception, but there are two different instructions before subtract which haven't completed their task. So what you're going to do is, if the subtract generates an exception in the reservation in the reorder buffer entry, because subtract hasn't completed its task, so you wouldn't have some result over here, but there would be some other field along with that entry which is going to tell us whether an exception has been generated that by that particular instruction. So we are just going to say yes, subtract has generated an exception, and there won't be any result because it has generated some exception. So we have to handle that exception first, and then we are going to come to. So this means, again, if a later instruction is going to generate an exception, it won't be serviced yet. So we are just going to um, store that status that an exception has been generated, but we are not going to actually service that exception at this point of time, right? We are going to service that exception whenever that instruction's turn comes for commit, whenever we know that this is no more speculative, right? So what we are going to do, we are just going to just store this status that this instruction while its execution has generated an exception, but we are not going to handle the exception yet because this instruction has not come to its turn of commit. We are going to complete our divide and say divide didn't generate any exception, so we are then going to complete our add, then we are going to complete our multiply, then we are going to come to subtract and see that it has generated an exception. Now we are going to handle its exception, and then we are going to come back to the next instruction after subtract. So this is going to ensure that exceptions are always going to be precise. If only we ensure that the results are not written before the program order, before that instruction's turn comes in the program order, if run on a sequentially executing processor, right? So this is the thing that we are going to discuss over here in exceptions. So not recognized until it's ready to commit. This is the second case. If a speculative instruction raises an exception, the exception is just recorded in the reorder buffer entry. So if you later find out that instruction shouldn't have been executed, then you can just remove that instruction from the reorder buffer, right? So we call this scheme as the Tomasulo's algorithm with reorder buffer, or sometimes as hardware-based speculation. So both are the names here. So it's actually Tomasulo's algorithm from our last lecture, but we have just introduced one more structure over here, which is the reorder buffer. As you can see here, the instructions would be coming again in the same order. Reservation stations would have an additional field which would be the reorder buffer entry, and the common data bus is still there. The common data bus is going to broadcast the results, and this result this time is not going to broadcast the reservation station name, rather it's going to tell the reorder buffer entry number, right? So let's come to an example to make things clear. This would be the structure when this would be also visible in those slides. We are going to work on this particular program here, right? So this program has a load, add, divide, branch not equal to 0. And so what I'm going to do is I'm going to just take a snap of this particular programs if we need that, or just remember I'm going to just come back to 12 if needed. So I'm going to just go through that, right? So let's start. Now for our own ease, so what we are doing is so that program is not over here, so we can refer it back whenever we need. So this is our structure here. So this is the reorder buffer. This is the main thing. This is the new thing, right? This is a new thing that has been added. So whenever a floating point whenever an instruction is going to come, that's going to come in order. So these instructions are maintained over here. So the instructions are coming one after one another in a particular cycle. Let's come to these fields over here. So this is the instruction field, right? This is going to tell you which instruction is currently in the reorder buffer. This is the value field, which is going to hold the result. This is the status field or done field, which is going to tell you whether this instruction is ready for commit or has completed. These are the reorder buffer numbers or the entry names. And this is the destination field, which is going to tell you where in the register or memory location this result is going to be written, right? The remaining things are simple. These are the registers, actual registers, and they are going to write their results according to the commits. So commit is going to happen for this first instruction first, right? And the reservation stations are as they were previously, except that we have added the destination here, which is the reorder buffer number. So so wherever that result is going to go, that is going to update. That's going to be updated over here. So this is the first cycle. Now in the first cycle, we have issued the first instruction, which is the load instruction, right? So I'm just going to come back to my program over here. So this is the load first, and then we are loading to F0 with the register contents with the address as 10R2, right? Then we have an add, then we have a divide and branch and load and add and store, right? Now, let's say this load has resulted in a miss, but the second load it has not resulted in a miss. Rather, it was there in the cache, and so we can execute this. We can start executing this load, but for the previous load, we have to wait for it. Now, this would mean that since add is waiting for this load only, so add can start its task, and the store can also start its task. But this add, the one in the previous one, it has to wait because since this load is not available, so F0 is not there. So this is just to ensure that what happens when later instructions complete first, right? So let's start this. Okay, so this is the first instruction over here. Okay. Now let's in the second cycle, what's going to happen is we are going to issue the add instruction over here. Now the changes that we are doing over here, so add instruction is going to go to the add reservation station. Load is going to go to the load reservation station. Okay, I forgot to tell that in the previous slide. This is the loads reservation station. Let me just point pen. Right. So this is the load reservation station, and this is cycle number 1, right? This is cycle number 1. I have not named that because we are going to go through that quickly. So this was the first instruction that we issued. So this instruction is basically talking about the load. So it's going to go to the load reservation station because it's going to update F0. So we have mentioned here the register name F0, which is going to be its actual destination. So when its turn comes for commit, this result, whatever that result is going to come over here, it's going to be updated in F0, right? Now in the reservation station previously for load, we just stored the address. Okay, but here what we are going to do is we are going to store the reorder buffer number entry where this result should go to. Okay, so reorder buffer or ROB1, the reorder buffer 1. So ROB1 is the name of the entry where that result has to go. So whenever that result is available from memory, it's going to be broadcast everywhere. So it's going to go over here and here. So anyone who is waiting for ROB1 is going to take that result. So since it mentions that the destination is ROB1, so that result, whatever that value is, which is going to come from memory, is going to be stored in the value field over here. And since this is the first instruction, so this should be the first to commit. So whenever that result is available, it's going to be updated in that particular register, right? So let's come to the next instruction cycle where we are going to issue add. Now you can see the changes over here. This is our second cycle. What happens is, here is we have issued another instruction, and since this instruction updates F10, so the destination register name is mentioned over here, and you can see here add is going to be executed on a floating point adder. That's why we are going to talk about the reservation station related to add. Okay. Now in this reservation station, again, there are two fields, F4 and F0. Now we are going to look over here in the destination field if there is any reference to these registers. So we are going to just copy their reorder buffer number entries in the reservation station. So we see for F4, so since F4 is not here, this means F4's value is the current value in the register. So we are going to take that value, fetch it from that register, from the register file. But for F0, we see that F0 value is still here. So it is here in the, this means that F0 value in the actual register file is an older value, right? And we need to fetch this value from ROB1 whenever that value comes. So instead of F0, we have mentioned here ROB1. Now, whenever this result is available, it's going to be broadcast everywhere. So if any reservation station is waiting for that, it's going to take that result and then it can start its execution if both the operands are available. Now, since this is add and it's been issued in this entry ROB2, so you're going to see here that a reservation station has got this additional field which is going to mention which reorder buffer entry is this result going to go to, because it's going to be an add result, so it's going to mention here ROB2. So anyone waiting for whenever this result is available, it would be broadcast as that data plus ROB2. So the destination would be ROB2. So it's going to be updated in this particular field over here whenever it's executed and it finishes its execution. Okay, so and I'm going to take some questions. So because I've just discussed two instructions, are there any problems here? No. If there are any problems, you can
Excuse
ask
me,
any
sir.
question. G.
Sir, what about the first instruction, the load? When will be the result of the load available to the ROP1?
Yeah, actually, it takes about say 2 cycles for that. But let's say this first instruction is a miss. So this means it's going to take many more cycles. So we don't know how many cycles are they going to take for this particular instruction. But let's assume that load is waiting for this result from main memory, and if load is waiting, then add also has to wait. So we are just going to see how can programs later instructions start their working even with the previous instructions waiting for their results, right? So this is our assumption that we are making, that this load is not getting its result anytime soon, but the next load, which is mentioned over here, the next one here, this is going to finish its task earlier. So this one is going to finish its task earlier, and this is not going to do that. So we are going to see how this is going to move, right? So now let's come to our third instruction. Um, Third instruction was divide, and likewise what we are going to do is we are going to do the same thing. Since updating F2, so we have mentioned F2 as the register destination, F10 and F6. So let's look. F10 was over here, so F10 is about ROB2. So when divide is going to come to the multiplication reservation station, F10 F10 would be replaced by ROB2. And since F6 is not over here yet, so this means that F6 value is current over here in the register file. So we are going to take that value and store it over here in the reservation station. So this operand is available, but this is waiting. And since divide is going to is in the third entry, so we are just going to mention the destination for this result as ROB3, right? So these are three things that we have done. And likewise, we are going to do it for the next instruction. So what I'm going to do, if this is all clear, so I'm going to skip some cycles, right? So I'm going to skip some cycles and move ahead so that we complete some more of those reorder buffers. Right, so likewise we have done it for the, so you can see here branch does not have any destination, so this field is empty. Then there was the second load that we saw that we said that this load is going to complete earlier, and then they have an add over here. So up till now what we have done is till this point. So we have fetched till this point. So next instruction should be the store instruction. Okay. And the fields have been set accordingly, so you can go through that as well. So let's do the next one, right? Let's do the next one. Okay, right. This is a store instruction. Now store is just going to write the result to the memory, so there is nothing about execution over here. And for store, so what we are going to do is, since store was talking about f4 value to be stored in that particular um, memory location, so what we are talking about is where are we going to get f4 from. So f4 is going to come from rob5, so we have just updated the value over here as rob5, right? So whenever that value is going to come, this is going to be going to the memory. So you can have a memory over here as well drawn, so rob5, and this is also connected to this. So this is going to go whenever that store's turn is going to come, right? Remember that. That's the new thing, commit. Okay, and nothing more over here. Okay. um, right. So now let's say that this store result is available. So this rob5 is now available. Now who is waiting for rob5? So let's first of all see. Now in the next cycle, this result would be broadcast. Okay, so whoever is waiting for rob5 is going to get the result. So this add is going to start this result because it's going to get both of its operands. And who else is, so this entry would be removed. Okay, so we are going to have this entry finished because this work has been done. Done is going to change. Okay, and anyone else, yeah, this is waiting for rob5. It's going to update itself as well, but it's not going to actually write to the memory until its turn comes. So these are changes that are going to happen. So only add is going to
Excuse
wait
me,
for
sir.
G.
Sir, the value ROB5 is only available due to the store instruction.
No, rob5 is also over here. rob5 is also required by add instruction to proceed, right?
But
So
sir, just now, right now we have started discussing the ROB value
no,
ROB5
actually
after
not
executing the
in this
instruction
cycle.
store.
No, not in this cycle. Not in this cycle. I was just asking you what is going to happen if rob is going to be broadcast in the next cycle, right? I was just asking what happens in the next cycle, so we know what's going to be changes in the next slide. So whenever this is going to broadcast as a result, this entry would be removed. The values of rob5 would be stored over here and here. So because this add has got both these instructions ready, so, both its operands ready, so now it can start its execution in the adder, and whatever time it's going to take, it's going to just start its value, and then it's going to move in this way. So we are going to see that load is going to finish earlier, is going to execute earlier, the second load. Add may also execute earlier. Store cannot execute because store's execution means to write the result in the memory, and this is not going to happen until its turn comes for commit. But we are going to have some results over here. We are going to have some results coming in the reorder buffer, and for some earlier instructions we are still not going to have any result, but for later instructions we are going to have our results ready. Okay, yeah, any questions here? Okay, now let's move now. So this is what's going to happen in the next slide. So let's go to the next slide. Okay, so as I mentioned over here in the previous slide, no more entry for this second load. This load has now broadcast this result. Add receives that results. We are going to call that as R3 because that load was working on R3, right? And this load gets its value, whatever that value is. So all these three fields have been updated simultaneously. The add gets the result, the load gets its value, the store gets its value. Okay, because these were the three things that were waiting for rob5's result. Okay.
Sir, in this case, the MR3 is represented by the value of ROB5.
Yeah, it's actually the memory memory content. So
Of
we are
R3.
just of R3 as an address, right? So it's just, if for example R3's value is 1000, so um, whatever is stored at location number 1000 in memory, that value, let's say 74, so that value would be copied on all these places. So 74 is going to come in all these three places.
Got it, sir. Thank you.
Okay, right, any other question here? Okay, so let's move. So now what's going to happen is since add has got both its operands available, so you can start its execution, right? So now add can start its execution, and because we have just shown 6 entries in the reorder buffer, so if there are other entries and there obviously the program is not only about 6 instructions, the program has got many instructions, so all those instructions are going to start issuing, are going to be issued, and they are going to be dealt with in the same way that if the reservation station entry is empty, you're going to schedule them in the reservation station and give them the reorder buffers as we have done it for the previous cases. Okay, so in the next cycle, execution has started, right? And now let's say that this add has also completed its task and load has also completed its task, right? So when the add has also completed its task, it's going to update its value over here, and when this load has also completed its task, is going to update whoever is waiting for ROB1. So this previous add is waiting for ROB1, and obviously this field has to be updated and nothing more. Okay, so let's say these two things are going to happen. So if add is going to complete, then this entry is also going to be free, and if load is going to complete, this entry is also going to be free. We are going to get some value over here and over here. Okay, and that's going to happen in the same cycle, because you are going to get 2 results over here. Okay, so both of that happened at the same time. So these results were available. Memory got its result. Floating point adder also completed its result. So both were broadcast at the same time. And anyone waiting for ROB6 or ROB1 is going to update itself. So we have the value available for the first load now, right? And so in the next cycle, this add can start. But the important thing over here is this was our first instruction. And if we get a result for a first instruction, this means that this register can now be updated, because this is the instruction which is at the head of our ROB, which means that this is the first one to commit, right? So this is going to be the first one to commit. Okay, so if that result is available, you are going to update F0. So you are going to update F0 with this value. Even though we have these values available for the later instructions, but we are not going to update F0 or F4 in these cases. But whenever their turn comes for commit, then only we are going to update that particular register. So what's going to happen is now we are going to commit this particular instruction. So commit means this is the last step. Whenever commit happens, then you are actually going to write that result in the register, and then you are going to free this ROB, this reorder buffer entry. So this is going to happen, and then you are going to start execution. So you have your results available for F0 and F4, but you are not going to update them until their turn comes for commit, and the turn for commit is going to be always in order. Right? So this was about Thomas's algorithm with reorder buffer. Any questions regarding this? Any question? Anything that you? So for example, if I give you a scenario that this is my program, and you can always find the dependencies between instructions, and I ask you to do the same like we did over here, to show how the program is going to proceed in the cycles, in the next 4 or 5 cycles. So I hope this would be easy for you people. So we are going to go cycle by cycle, and we are going to see how an instruction is going to be issued when is going to be going to the reservation station, and how are the reorder buffers entry going to be updated, right? So I hope this is okay. If there are any questions, you can ask
Same,
me.
sir.
G,
Sir, kindly solve a scenario of this kind of program to this algorithm.
kindly what?
सर बिकॉज हियर वी आर सर कोई एक क्वेश्चन हमारे पास इस सिनेरियो का सॉल्व किया जाए तो ज़्यादा बेहतर है क्योंकि यहाँ पर जस्ट हम एजम्पशन कर रहे हैं कि
I
ब्रॉडकास्ट
cannot
हो
I,
गया
I cannot
नहीं.
hear I cannot hear you properly. Can you repeat it? There is a lot of noise coming.
Sir, kindly resolve another program like this.
Yeah, you can do it yourself. You can do it yourself. Try to do that experiment yourself. I've discussed one of them. You can make your own program. I'm going to come to a small program as well that you can run as well. It's available, and you can give your own
Same,
schedule. You
sir.
can give your own instructions and try to see how that instruction goes through at each cycle.
So here we have done all the steps just on the assumptions. So
Which assumptions? So
like the
whenever you yeah the only assumption that we had was that the second load is going to complete earlier than the first load. So whenever it comes in the program, you are always going to be given some kind of an assumption like this, that this instruction is going to complete earlier, or this is going to finish earlier, and then start from that point of time, right? So I'm going to come to that as well. There's a link in the slide as well. There is a short again, it's like an applet in the previous lecture. There is a small program that you can execute yourself to see how instructions are going to move. So if you are finding any difficulty, go through that, write your own instructions, give their timings, and see how it's going to move, right? So this Thomas's algorithm with reorder buffer also avoids those typical memory hazards. So we are, since we are going to just go through to the memory address, so we are going to ensure that the var and wav hazards to memory are also eliminated. So because we are going to update them with their own actual addresses, so this is going to eliminate that as well. Go through that. What I was talking about was this particular link shown at the top. This is a program developed for to simulate the reorder buffer, so you can have your own instructions mentioned over here, right? And you can also define whether which instruction causes an exception in C, and you can set their delays, their timings, and try see how they execute. So it's going to give you the results like this. The reorder buffer head and tail would be mentioned over here, which instruction is there and which is busy. This is the reservation station for add and multiply, right? So these are also there. Here you can see here that we are mentioning the reorder buffer number, right? So this is mentioning the reorder buffer number not as ROB but as number 3, for example, this one here, right? So this is going to state the register status, which registers are updated and which are not. So you can just go through that yourself, right? You can do that yourself. I don't think so it's going to be very difficult. Okay, so if there are any problems, if you want to execute your own program, you're going to see how it's going to go through the different sides. This is a good simulator, right? So that comes to our last topic for instruction level parallelism. There was another topic that I have skipped for this particular online class. That was about multi-issue processors. Normally after instruction level parallelism, I go to the multi-issue processor where I talk about the superscalar processor and the VLIW processor. So VLIW stands for very long instruction words, and superscalar processor and VLIW processor issue more than one instruction at a time. So I leave that as a reading assignment for you. So you can go through that yourselves. I'm going to come to the last topic, which I'm going to also continue in the last lecture, and that is data level parallelism. Now, up till now, we have discussed about instruction level parallelism. Now we're going to talk about the data level parallelism. When you're talking about instruction level parallelism, we're talking about instructions that can execute simultaneously or have some overlap in between them. When we're talking about data level parallelism, we are trying to find out parallelism at the level of data, where you are talking about instructions which where you just need to execute one instruction on multiple items. And this is a very common scenario. For example, if you want to um, add um, a scalar to all elements of an array, right? So an array is something where you have got many items, many elements, but all of these elements have to be added with the same scalar value, right? So a program for that is going to have some kind of a loop where you might have one or two instructions, but it could be something like this, where you are talking about adding that scalar value to all elements of that array, right? So what you are going to do is you are going to add that scalar value to an element which has an index I, and then you're going to update that index over here, right? So you're going to update, sorry, you're going to update that here. So it points to the next value and next value and next value. So this is how it's occurring, right? But if you're going to convert that into an assembly language, or if you can see from this instruction, so you can see here that these elements are working independently from each other. So they are not worried about the results of their previous iterations. So anything that's happening in the loop, so all the iterations of the loop are independent from the previous iterations of that loop. So we call such a loop as sometimes as a parallel loop. So this kind of a loop can be easily vectorized. So in another way, what I'm trying to say is if every element of these array are independent from each other, this means you can do these tasks in parallel. So that is, you can do these two things at the same time. So AI and AI plus 1 can be done at the same time, right? Even AI plus 2. The only thing you need is functional units. So if you have got two different adders, then you can do these two operations in one cycle, right? Now when you're talking about data level parallelism, we are looking for such kind of parallelism where we can process many elements together at the same time. For data level parallelism, our main thing that is required is we need many functional units. So we are talking about many functional units. So instead of just one adder, we are talking about having many adders, right? So this is our main goal here. So we are going to have many functional units, right? And we are going to give them data, but we are going to have the same instruction on all of them. So if there are two adders, one of them is going to work on one element, the other is going to work on another element. So both are going to add, right? Both are just going to add. So this would be a single instruction. So sometimes we call this as a single instruction multiple data, SIMD, right? Or many data. So single instruction means a single instruction would be there, and you are going to apply that instruction to multiple data elements. And then single instruction means that control unit is just going to issue one control signal, and it's going to be applied on multiple data items. The main thing in all these data level parallelism technique is that it has to be a single instruction. So a single instruction is required by many elements. So all these elements can then work together. Okay. The other thing that I've just discussed, that these elements should be independent from each other, so they don't actually work together. Now, if you're talking about data algorithm, before that we have to discuss something like vectors. So normally up till now what we're discussing was scalar, a single element. Now we are talking about vector, which is a set of scalar data items, all of the same type, stored in memory. So we have a vector processor which has got hardware resources to work on these elements together, and vector processing is then called as the whole term for all those operations. So when you're talking about a normal scalar, we are going to have an instruction like this where you're going to add R1 and R2 and put the result in R3. When you're talking about vector operations, which is topic over here right now, we are talking about doing it on many items at the same time. So a single instruction would be there, but there would be many functional units. So and these elements, all these elements would be added with their corresponding entries in that vector register, right? So there are different other elements over here. So we have got many arithmetic operations, and where are we going to apply that particular technique? So all those large scientific engineering applications, they have these kind of data which require processing of the same kind at the same time. So if you have got many functional unit, you can apply that single instruction to all of them, and they are going to work on different data elements at the same time, and this is going to enhance the performance. So instead of doing one element at one time, if you're doing many elements at one time, this is obviously going to be very beneficial. The other thing is the multimedia application. So in many image processing and video processing algorithms, what we do is, whenever we do it for a single pixel, we have to do that for all the remaining pixels as well. So if you're talking about applying a kind of filter, digital filter to a particular image, it's going to work on the neighborhood of that particular pixel, but this has to be done for all the pixels. So again, something where we need parallelism over here. So these multimedia applications are also going to benefit from that. When you talk about single instruction, multiple data, there can be two different types. One is where you have a single CPU, right, and we have got many multiple functional units, or we can sometimes call them as processing elements, right? And each processing element has its own memory. So we have got multiple ALUs or functional units, and they have shared memory, or they have their own memory. So this is also called as a true SIMD. We're calling it true because there are multiple functional units here. Then you can have a pipeline SIMD. And in a pipeline SIMD, what happens is we have again a single CPU, but the functional unit is pipeline. So instead of having multiple functional units, we have a single pipeline functional unit. So a pipeline functional unit can also have overlaps and can also execute multiple instructions, but it depends on the depth of this pipeline. So if the depth of this pipeline is 6 stages, this means you can have 6 operations happening in parallel. So the first is still going to take 6 cycles to fill the pipeline, and after 6 cycles, you are going to see that there are operations coming one after another, right? Okay. Now, when you're talking about data parallelism, there are 3 variants historically. One is the vector architecture, and vector processors were introduced in 1970s, around that era. Then in 90s, some kind of vector processing was started by Intel with their techniques called MMX, or multimedia extension. These were special instructions that were used for having doing multiple operations at using a single instruction. So this was mainly for multimedia operations, so they called that as multimedia extension. So anyone who was trying to work on multimedia operations could use those instructions to enhance their their program's performance. Later on, they also introduced some new instruction sets, which were extensions for the same MMX technology, but more of them. So they didn't remove the earlier ones, they just introduced more to them. So that were called SSE. Later on, they had more of them added. So they kept on increasing those instructions. So they were basically more of those instructions, so programmers or compilers could use those instructions to enhance the performance of multimedia applications. These days, that has been replaced by GPUs. So GPUs are also a kind of a vector processor. You can say they work in the same way that you have a single instruction and multiple data items or on which that instruction is going to be executed, right? Or advanced or that those advanced processing units which are also um, working for graphics, right? So GPU is the graphical processing units, which are mainly developed for multimedia applications, enhancing the performance of the games, or because it's a very big industry, the gaming industry. So you need high processing, and also the same thing that you need those tasks which have to be done for all the pixels at the same time, right? So for that you need many functional units. I'm going to come to GPUs and SIMD extension in the next class. Today we are going to talk about vector processor in our remaining time. So we have got an hour or so. So what are the properties of vector processor? So when you're talking about vector processor, a single instruction is doing a lot of work. So a single instruction specifies a whole loop. So you have a single instruction, and that is determining, or that is basically a whole loop that is going to work. So as I mentioned over here in that in the previous case over here, is that if you need to add a scalar to an element in a vector processor, this whole thing is going to go as a single instruction. So you might have just one instruction for this whole operation, right? And computation of each result in the vector is independent of the computation of other result in the same vector. This is the main thing. So if you're talking about vector processors, one operation is independent of another operation. So if you have got multiple operations, if you have got a vector processor, you have structures for only holding the data items. We call them as vector registers. Now each element of that vector register is going to work with the corresponding element of another vector register. So this would ensure that it's not going to affect its result with any other element of the another vector register. So this in a vector processor, this is important, that computation of each result is in the vector is independent of any other computation of another result. Okay, so between the vector instructions, there are checks for data hazards, but not within the vector register. So between the vector register, you can have hardware checks for determining whether these two instructions can go along together. And vector processor accesses the memory with known patterns. Now, this is also good because we are always talking about either fetching it in a row major order or a column major order. So even with column major order, there is a known pattern. So if you're talking about doing a vector processing on a matrix where you have got many elements, and if you, for example, want to multiply two different matrices, so what you're going to do is this row has to work with a particular column. So what you're going to do is you're going to fetch the whole row in a vector register and this whole column in a vector register. Now this vector is going to be placed in memory in either row major order or in column major order. Now, if it's placed in memory as in a row major order, since you are accessing the whole row at one time, so all these elements would be contiguous, right? To contiguous, they are going to be stored in contiguous memory locations. So again, the order is that all of them are with a difference of one memory location from each other. Again, a pattern. And if you're talking about elements which are in a column and stored in a row major order, again there is a pattern, because the first element would be here, the second element would be here, the third element would be here, and the distance between these elements would be a fixed distance, right? So if the first and second has a distance of a, the second and third also has a distance of a. That this is again a pattern, right? So even for row major order or column major order, there is always a pattern. So in a row major order, the pattern would be that everyone has a distance of 1. Here, everyone has a distance of a. Now, when you're talking about vector processors, so it always accesses the memory in a particular order, which is good, because this means that you can apply different techniques to fetch different elements from the memory, right? The fifth point for a vector processor is that the control hazards due to loops are reduced because there are fewer instructions. This means that there are going to be also fewer control hazards. Because there are going to be fewer branches, there are going to be fewer control hazards in the program as well, right? But there are going to be control hazards. You cannot eliminate them, but they are going to be less than a normal program. Now we are going to talk about basics of vector architecture in this lecture, and then in the next lecture we are going to talk about the SIMD extensions and the GPUs. So when you're talking about a vector processor, it's not only a vector processor alone. You need an ordinary scalar unit as well. So for a vector processor, you need the scalar vector unit as well as a vector unit. So vector unit is an additional thing, but you cannot have only a vector unit, right? You always need a scalar unit as well. Now, some of the examples in history, because vector processors were earlier in 70s. These days there are variations, but for those variations you need to understand the earlier processors. They were vector processors which were designed which could work from memory to memory. So they just got their operands from memory and stored them in memory, right? So that architecture was also there. Then there were some architectures which were registers specific. So every memory element has to be fetched first of all in a register, and then you have to work on those registers. So CTC is an example of a memory to memory vector processor, and Cray1, the Cray series, is an example of vector to register architecture. So we are going to take an example for understanding the vector architecture by changing the MIPS processor that we have studied, the 5-stage MIPS processor, and we are going to make that as a vector processor. So what changes are required for VMIPS? The first thing that we need is vector registers. So for any vector processing to happen, you need to have vector registers. Now, typically what happens is that this vector register, when you're talking about vector register, it's a very big register. Now, and that register at least has got 2 read and 1 write port. So typically what happens is this register has got 8 to 32. So you in a processor, there are 8 to 32 vector register, and each register can hold 64 to 128 elements, each of 64 bits. So a double precision number. That's the most you need. So if I say we have 32 vector register, and each one of them is going to hold 128 elements, right? And each element is of 64 bits. So if you do the calculations, this is something like in terms of bits. So if I want that in terms of bytes, then instead of multiply by 64, I can just multiply by 8, or just you can at the end divide by 8. That's again same. So we have a 2 raised to power 5 over here, and a 7 over here, and 2 raised to power 6 over here. So you can just add all of these powers. So 12 plus 6, 18, and then finally divide by 3. So 15, that would mean 2 raised to power 15 bytes. 2 raised to power 15 bytes means that this has a space of 32 kilobytes. So you need a register file of 32 kilobytes, right? You need a register file of 32 kilobyte where each register is holding 128 elements of 64 bits. Now this is just the vector registers that you need, right? Now for our VMIPS, we are not going to go for 32 vector registers. We are just selecting 8 vector registers from V0 to V8. Each can hold 64 elements. So we are just taking the 64 elements for our vector size of 64 bits, right? So we need 16 read ports and 8 write ports for our 8 vector registers. Now, along with vector register, what else do you need for a vector processor?
Excuse me, sir.
G.
Sir, there is electricity problem, and the battery of my laptop is going to be running out, so
Yeah.
I might be offline.
That's okay. That's okay. But you can just go through that video recording, right? Okay. So vector functional unit. So a vector register is our first thing. What else do we need? We need functional units, vector functional units. So these are the main thing that I've discussed. That there could be a true SIMD approach. There could be a pipeline SIMD approach. True SIMD approach is a little complicated. It takes a little more hardware and increases the cost, but has more performance. So, but we are going to go with the pipeline SIMD approach. So we are going to have fully pipelined separate functional units. So they are going to be different functional units for different tasks, and these units would be pipelined, right? So in a VMIPS, what we are saying is we have 5 functional units, and these functional units include the floating point add subtract unit, the floating point multiply, floating point divide, integer unit, and logical unit. So we are going to have 5 functional units in the processor that we are trying to build. Now the third thing that we need is a separate load store unit. So instead of having just one read operation, we need to read the whole vector register as a single operation. So we need a special load store unit. So the same load store unit that was working for a scalar is not going to be helpful for us, because we are talking about reading into a vector register which is holding 64 elements together. So for that, and also we have just discussed that it's going to read with a particular pattern. It's going to write or read with a particular pattern. So for that, we need special vector load store unit. The fourth thing is the scalar register. So we have talked about the vector register, and scalar registers need to be there as well. So you cannot just have vector registers. So we are going to have the same scalar register. So we have got 32 floating point and 32 general purpose registers, which we are going to denote by R0 to R31, and the floating point registers as F0 to F31. So these are still there. So these registers are there, but the vector registers are more to them. So they are we have 32 general purpose and 32 floating point registers, and along with that we have got 8 vector register, which we are going to denote by V0 to V7, not V8. So V0 to V7, so that would be 7, right? And then finally, what we need is a crossbar to connect all of these structures together. So if we have all of that, the structure that comes is something like this. So we have a main memory connected through a vector load store unit. That's a special vector, and these are the additional vector registers. These are the older scalar registers, and these are the new functional units, and these are pipeline, right? And their stages are different for each of them, right? Okay, you can get more of these instructions from the book yourself, but I'm just going to give you a quick look at some of the instructions, some of the vector instructions that can be designed. For example, if we need to add two vectors together. So if we need to add two vectors together, what do we mean by adding two vectors together? Now, if you're talking about adding two vectors together, like v1 and v2, if you need to add v1 with v2, what we are talking about is each one of them has got 64 elements. So each one of them has got 64 elements. So if you need to add vectors together, what we mean here is the first element is going to add with the first element of the second vector register, and it's going to be stored in another vector register as its first element. So that result is going to be stored over here. So we are actually talking about adding these two elements together, and then storing the result as the first element, and again the second element with the second element of the second register, and storing them as the second element of the third register. So for that we have an instruction add vv. So add vv means that add vector to vector, right? So these are the suffixes that we have added to the common instruction. So this makes it clear what this instruction is supposed to do. So vector means you are going to have two vector registers over here, and obviously if you have a vector register, then the result has to come in a vector register. So that's implicit. So so there are three vector registers, and you want to add two vectors together. Now if you want to add a single vector with a scalar, so you want to add all the elements of that vector with a particular scalar value, then for that you have another instruction which is add sv, or it could be add vs as well. So both these instructions are possible. Here we are talking about sv or vs, which means you need to add a scalar to a vector or a vector to a scalar. Now if you are writing an sv, so you need to have this scalar quantity defined as a floating point register, right? Not a vector register. So this floating point register is holding the scalar. How this is going to work? It's going to you are going to have one vector register and another as a scalar. So when you're talking about like this, then this means that all these elements are going to be added with the same scalar, and it's going to be stored in a vector register, right? So you are going to add the first element with that scalar and store it as the first element of the result, and the second element with the scalar and store the second element, and so on, right? Right, and if you have written add vs, that's also possible, but then you need to have the vector register as your first operand and the scalar as your second operand, right? It doesn't matter for add, but maybe for subtract, you might need to subtract the scalar quantity from a vector, or you need to subtract the vector from the scalar. So that it's a little different. Likewise, you can see multiplication here, the load, and then there are different types of loads over here. So this is a normal load, which means you are loading from the consecutive elements stored in memory. But if you want to load it with a constant distance from each element, you have a special instruction which is called as load vector with stride, right? And if you want to, there is another kind of load which is load vector with index. So you provide the index register, and it's going to take only those values which I mentioned in the index register. So there are different instructions. This is just a glimpse of all these instructions that are possible. Then we have another type of instruction which has got two different dashes mentioned over here. These dashes could be filled with any condition you want. This is the basic you can say branch instructions, or in another word, what you're trying to say is it's working for the conditional operations. So if you fill these two gaps, these dashes with say ne, So this instruction would become SNEPV. NE, where NE stands for not equal, right? So what you're talking about is if these vectors are not equal, then it's going to set a mask. So this instruction basically sets a mask for a particular register, which is called as a mask register. Now more details there in the book, so I'm not going to go into details of each of these instructions. But what we are going to do is we are going to write a program, a simple program, which we are going to call as DEXP. DEXP is double A into X plus Y. So this D stands for double A into X plus Y. So we call that as DEXP. Now DEXP program, as you can see here, is actually the program Y is equals to A into X plus Y, where Y and X are both arrays. So Y is an array and X is also an array. So what you're doing is you are taking an element of an array, multiplying it with a scalar, and then adding it with the corresponding element of another array, right? So if you want to write a program for that in a normal processor, a scalar processor, if you're talking about in terms of vector and scalar, what you're going to do is do something like this. Okay, so I'm going to just briefly go through this program because it's simple, so you don't just really need to go into detail of that. So what we are trying to do, first of all, if you want to do this, then what you do is you load the value of A into a vector register, into a floating point register. That's our first instruction. Then we set our limits and store that in R4. Where are we going to stop? Because everything is in the memory. So you need to define what is going to be the last address, because the loop is then going to run till that point. So this instruction is for the last address that's there in R4, right? Now we are going to do this repeatedly. So if what we are trying to do is we are going to if I try to write this program for in a high level language, what we are trying to do is we are multiplying A with an array element I first, and storing that in yi and adding yi to that. So this is a single instruction, but of a high level language, and this is part of a loop. So this is going to run in a loop, and this loop is going to execute as much time as required. So if there are 64 elements, we need to run this 64 times, right? So for every element, you are going to fetch one element, multiply it with the A, and add the corresponding value of Y. Now, if you want to run this program, how are you going to start? You need to fetch the first element first of X, and then the first element of Y, right? So here it's what's happening is we are loading the first element of X into another floating point register F2. This is you have obtained the first element. Then you're going to multiply it with A. So if you're going to do it up till here, up till this point, you are finished with this particular step. Then you're going to load the first element of Y, right? And then you are going to add this with the result that you have obtained over here, which was stored in F2. So you're going to add F2 and F4, and this is going to give you this whole thing. Then you're going to put it back over here, so you're going to store it over here. So this is your main loop, these 5 instructions. So these 5 instructions are actually going to be the whole program for DEXP. But then it's not stopped over here. What you need to do is change the index, increment I, and the value of address Y, because they are at different addresses. So you need to increment both of their addresses so that they point to the next element. So in the next 2 instruction does that. And then what you do is you are also going to subtract it from R4. So R4 is going to contain the bound where it has to finish, and so you are going to check whether you have reached the last result. So what you're doing is you are subtracting a value of R4 Rx, which is going to be subtracted in every iteration, and then you are going to put that value in R20. So if that value is going to reach 0, this means you have to stop. Until that is not 0, you are going to then loop again, right? So if it is not 0, you are going to do it for the next element. So it's going to be 0, R20 is going to be 0 when R4 minus Rx, if both of them are equal, right? So what you're doing is adding the value of Rx by 8 each time, right? And then you are going to subtract that with R4 and put that value in R20, right? So you're just checking whether you have reached the end of that loop. Now this is for a single instruction. This is a program having many instructions, right? And if I ask you to calculate how many instructions are there, you can just do that. It's simple. You can have just count two instructions over here, and these are repeated 64 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 2 plus 9 into 64, right? So whatever that result is, what's the result? 9 to 64 plus 2. That would be something like, how much is that? Yes, anyone? 640 minus 64 would be something like, yeah. What's the result? Can anyone give me the result? Okay, let's open. You people are not going to talk anything. Talk about anything.
1152, sir.
No, not
578.
578. Yeah.
Oh, sorry, sir.
Yeah. Okay, it's because 64 into 10 would be
Yes,
640.
yes,
so you just have, 64 into 9 plus 2, 578, right? So 578 instructions. And if you talk about, these are dynamic instructions, 578. So 578 total instructions. If you talk about the static instructions is about how big your program is when you are going to copy it in the memory. Dynamic instructions, how many instructions you are going to execute actually, right? So both counts matter, because dynamic means actually how many instructions are going to execute. So this depends on the, this is going to tell you about the execution time. Static instruction is helpful to know how big your program is going to be. So static instructions are 1, 2, and 11 instructions. Okay, so 9 plus 2, 11 instructions. Now, if you want to do that in a vector processor, this program is going to be something like this. The first thing that you're going to see is there is no branch instruction in this code. And let's go through this. Now, this instruction is the same instruction, right? So we are again going to load A into F0. But the second instruction is doing the load for the whole value of the array X into a vector register V1. And how can we do that in a single instruction is because we have got 64 elements and this is holding 64 elements. So what we have done is we have just given it the first address, and it's going to fetch the 64 different elements from those first address and put that in V1, right? So it's simple. The second thing we have done is we have multiplied F0, which is the value of A, and that is multiplied with every element of V1, and it's stored in V2, right? So this is the whole thing which is going to do this operation, A into X1. So all the elements are now multiplied with F0. Now we are left with just to load the second vibe, this one here, as a single instruction, and finally add the result of V2 and V3 as a single instruction, and then finally store it, right? Now, if you can see, the static instructions are just 1, 2, 3, 4, 5, 6, just 6 instructions. Dynamic instructions are also 6. So instead of 578, we have just 6 instructions in our program. We have to execute also 6 instructions for our program. But these instructions obviously are not the simple instructions that are over here. These are simple instructions, but here our instruction means a lot more operations. So let's talk about in terms of operations. How many operations are how many operations is the scalar program doing, and how many operations is the vector program doing? Now, when you're talking about scalar, so it's going to do as many operations as there are instructions. So there are going to be then 578 operations. So each operation being so a load is an operation, an add is an operation, and all of these are operations. Now, when you talk about vector, each vector instruction has got 64 operations inside it, right? So this first one is 64 operations, the second one is 64 operations, the third one is 64 operations, fourth, fifth, and sixth. So how many operations in total would be there? 64 into 6, which would be how much?
384.
384. Okay, so except the first one. Sorry, this is not the vector operation. Sorry, this is a normal load, right? So this is a single operation. So we have 1 plus 5 into 64, right? So this is the scalar only.
321.
Yeah, 321. Okay, 321. So 578 versus 321. So that the first thing that you see is in a vector processor, number of operations have been reduced, right? Second thing is the number of instructions have been reduced, right? And with no branch instructions, there are no control hazards, because this branch instruction is going to generate a control hazard, because you don't know which is going to be the next instruction. So you are going to wait and have some stall cycles over here. Then you're going to come over here, but here there is no wait over here. So if you summarize this, then we have a 1.8 times improvement in number of operations and 96 times improvement in the instruction execution, the number of instruction fetches. So 6 instruction fetches versus 578 instruction fetches. With every instruction fetch, there is a decode step as well. So we have reduced that as well. And then you have got 64 times less pipeline hazards, which is obviously because you have removed all the control hazards. So 64 times control hazards removed. Right. So few more minutes. Let's talk more about vector architecture. Because in the next class, I'm going to continue with SIMD instructions, and then we are going to finish this this whole course. Now, when you're talking about vector architecture, so vector instructions that can run concurrently are called as convoy. So in the literature of vector architecture, all those vector instructions that can be issued concurrently, that can run concurrently, are called as convoy. Now, for an instruction to be in a convoy, the first thing that you have to see is that there shouldn't be any structural hazard between these 2 instructions or 3 instructions. So if you want instructions in a convoy, this means these 2 or 3 vector instructions can execute or run concurrently. Now, for these instructions, it's a must that there shouldn't be any structural hazard between these 2. So if both of them are add instruction and you just have a single add functional unit, that's a structural hazard, right? So if you have got 2 add units, you can schedule 2 add instructions simultaneously. But if you have a single add unit, you cannot have 2 add instructions in the same convoy, right? That's the first thing. Okay, so and we are going to, for speeding up, we are obviously going to have multiple functional units that we have discussed, and multiple 2-ported register banks. So this means that you are going to also have banks in the register. So this is going to speed things up. If you are going to have multiple execution units, like for example 2 add units, then it's better to have your registers also separated in banks, so that one of the adder is going to always take registers of odd entries, and the other takes registers of even entries. So this is how you can schedule many instructions together. And we're going to talk about that separately as well. So these separate paths are sometimes called as lanes. Now, two instructions can be in the same convoy, as we have discussed it, if there is no structural hazard. But if there is a data dependency between these two instructions, can they move together? So if you have got two instructions and they are dependent on each other, can they be part of the same convoy? So that's the question. Like, for example, if I have an instruction like add vector, and I need to add two vectors, v2 and v3, and then I have got another instruction like subtract vector, where I have v4 and I need to subtract v1 with another vector v5, say, for example. Now, if I have a single add unit, so both add and subtract are going to use that unit, right? So can they be part of the same convoy? Now the first question is, can these two instructions be part of the same convoy if I have a single add unit, right? So the answer is no. The answer is no, because there would be a structural hazard. If I try to run both of these instructions together, there would be a structural hazard. Okay, so there would be a structure. Let's just talk about this case here where I have v6. So there is nothing common in both of them. So v1, v2, v3, v4, v6, and v5. So they are not dependent on each other, but there is a structural hazard because I have a single add unit. Now, if I have got two add units, then can they be part of one convoy? Yes. Why? Because I'm going to schedule add over here and subtract over here. So since they are not dependent on each other, I can schedule them separately in two different functional units, right? Now the second thing, now if I have a single functional unit, right, and instead of subtract I have a multiply instruction, which is obviously going to run on a different functional unit. It has got its own multiplier unit, but now it uses a value v1 which is computed by the add unit here. Okay, so there is a dependency between these vector instructions. So now the question is, can they be part of the same convoy? Now the answer is yes, they can be part of the same convoy. Now, but you would say for the instructions to be part of the same convoy, we are talking about running them concurrently. Now exactly, they won't be running concurrently, but there could be a scheme where what you do is, since you are working on one element at a time, and if you're talking about v1, you don't need all the elements of v1 together to be added with v5. So what you're going to do is you're going to wait for the first element's result to be computed. Now whenever that result is available, you're going to pass that, or in other words, forward that result to the multiplier unit, right? So that would be a little delayed, but once you have the first result, you can start your multiplication process. So if the first element has been added, then you can pass on that result so that the first element can be multiplied with v5's first element. And then you can see that most of them would be overlapped. So you are only going to wait for as much time as the depth of the ads pipeline. So if the pipeline has got 5 stages, so for the first 5 cycles, you are not going to get any result, but then you are going to get the first result. And as soon as you get this first result, you're going to pass that result to the multiplier unit, and then it's going to start its own working. So even though that is going to be a little delayed, but still we can say that these two can be part of the same convoy. So that's the question. So if there is a data dependency, then they can be part of the same convoy. They can still be part of the same convoy, but it depends on the depth of the pipeline. So it has to, the second instruction has to wait for a particular number of cycles, but then still it can continue. It would be still called as part of the same convoy. Now this is similar to the forwarding that we did in the pipeline processor, but in vector processor this forwarding is called as chaining, right? So in vector processor term, chaining is to provide the result of the first element and the other elements to the functional unit which needs that particular result, so that the other result can continue. Now when we are talking about having instructions in convoy, what actually are we intending to do with those convoys? Now when you're talking about convoys, we mean that we can schedule these convoys at the same time. So this means that we can give a figure of how much time is our program going to take on a vector processor. That figure would be a rough figure, but it's going to be helpful for us to determine that our program can be scheduled in a particular way in a vector processor is going to take such much amount of time. And that time is actually called as time. So the time taken by a particular convoy to execute is called as time. And for calculating that, we ignore the cost of that chaining that we have done. So the number of cycles that it has to wait, and also the depth of that initial pipeline stage, and we exclude that as well. So for example, if you're talking about these particular two instructions in a single convoy, you're going to see that normally there are 64 elements. So but it's working in a pipeline way. So in a pipeline way, what you're going to do is going to depend on the depth of this function unit and the other function unit. So let's say adds function unit has a depth of 4 stages and multiply has a depth of 6 stages. Now in actual term, what's going to happen is this process, adds process, the first element is going to complete its task in 4 cycle, right? And from there onwards, you are going to have one operation completed every cycle. So the number of cycles you are going to take for the whole operation is going to be 4 plus 63, right? Okay, because the first element is going to take 4 cycles till it ends the pipeline, and then from there onwards, every other element is going to take just 1 cycle. So 4 plus 63 cycles for the addition to complete. But then we said that multiplication is going to get its first result after the first one completes. So if it's 4 cycle, then it's going to get its result in the 5th cycle, right? So it's going to get its result in the 5th cycle plus the first operation is going to take 6 cycles. So the first one is 5 plus 6 or 11. So it's going to take 11 cycles to complete its task. The first one is going to wait for 11, and then the remaining one is going to take 63 cycles. So if you talk about the whole convoy, it's going to take 11 plus 63 because that's the last time. So 11 plus 63 is 74. So it's going to take 74 cycles to complete this whole process. But since there are 64 elements over here, roughly we say that it's going to take 64 cycles. If it's part of a single convoy, we take the time for a convoy as chime, and chime is the time of the whole vector processing. So it's 64 cycles roughly, right? So we ignore the cost of chaining and other pipeline depths, and we just talk about the time taken by the convoy, and that is roughly the number of the vector length that you have taken. So if the vector length is 64 elements, then you're going to say it's going to take 64 cycles. So I have just calculated the exact cycles. That was 74 to complete these two instructions, but roughly we are going to say that's going to take 64 cycles. That's a good approximation, because if you have got then m convoys, then it's easy for us to say that m convoys are going to take m chimes, right? And if each vector length is n, then this means that we are going to take m into n clock cycles, and this makes our calculation a little easier. So that is going to be added. If you want to be accurate, you need to add the startup times and the chaining times as well, right? But otherwise, it's for the chime, you are going to just talk about how many cycles going to take, and that is basically the vector length, right? So if the vector length is 64, chime is also 64 cycles. Okay, so let's do a problem over here, and I'm going to then finish today. So I'm going to take a code over here, and this code has got 5 instructions. So my question is, how many chimes will this vector sequence take, right? So the question is, how many chimes will this vector sequence take? And the second question is, how many cycles per flop of floating point operations are needed, ignoring vector instruction issue overhead, that is the pipeline depth. So the first question, how many chimes will this vector take? So in order to find chimes, we need to first of all divide this into convoys. So we need to see how many convoys are there in this code, right? Yeah, so for that, we have also mentioned that there is a single copy of each functional unit. That is, there is a single load store unit. So there is a single load store unit, a single add subtract unit, and a single multiply unit, right? So if you have 2 multiplication instructions together, that cannot be part of one convoy. If you have got 2 load store instructions together, that can also not be part of one convoy, right? So what's the answer to this? How many convoys can you see in this code? Remember, for convoys, you just have to look for structural hazards. If there are data dependencies, they can still be part of the same convoy by chaining. So you can always apply chaining, and then they can be part of the same convoy. Yes, anyone?
And 3.
3. So I'm just seeing that Iqbal Aziz is giving most of the answer. What about the rest of you? Imtiaz Saab, Yasir Ahmed, Altaf Ali Shah, Haider, Akash Ali.
Yes, sir, it's 3 because V1, V3, and V4 are common.
V1, V3, and V4 are common. No, it's not about V1, V2, V3. It's not about V1, V3, V4. No. Why 3? Anyone else? Imtiaz Saab?
Sir, I was disconnected during the intro of chimes, so I'm not.
So we've been talking about chimes. We say we can find chimes by determining how many convoys are there. And when we talk about convoys, we try to see instructions that can run concurrently, the instructions that can be executed at the same time. So how can instructions be executed at the same time? We just have to look for structural hazards. So if there are no structural hazards, then these instructions can be made part of the same convoy, right? So how many instructions, how many convoys do you see over here in these 5 instructions, and why? So Iqbal Aziz said 3. I didn't ask for any elaboration from him, but I just wanted others to give answers before I ask from Iqbal. Hi, Haider. Said Haider, you there? Haider, are you there? He's not responding. Altaf Ali Shah, Akash Ali. Where are people? Where are you people? Can you open your mic? Give me an answer. How many convoys are there? Where is Fahad? Fahad was here. Okay. Fahad, Shirina was here also. Shirina is also not here. Okay, so Iqbal, so it comes to you. Why 3 convoys?
Sir, because we have 3 single separate functional unit, and the load and stored can be concurrently working, and add is a separate unit and mult is also a separate unit.
Um, so if I'm going to divide them into convoys, which instructions are going to come in the first convoy?
That's the first one, load V.
Okay, only load is going to be first one. Why not multiply can be simultaneously with load? You are saying only for load would be there. Why can't load and multiply be together in one convoy? Serena, you were not there. My question is, how many convoys do you see in this sequence? Come on, I need some answers. Are you getting my voice?
Yes, sir. We are getting over.
Yeah, I know that, but I was just asking for that. Can you just also tell me what should be the answer for that?
Sir, V1 will conflict if we load and multiply place concurrently.
No,
So once
that's not the reason. As I mentioned here, you can have dependent instructions
uh,
part in the same convoy.
I mean that first we will do load, then wait, then we will do multiply.
Yeah, we can still be make that in the single convoy. As I have mentioned here, dependent instructions can be part of the same convoy. So the answer is 3, but which of these 3 instructions? So you just start with the first one, continue on till you find a structural hazard. Okay, so that's the trick. Okay, so I'm going to do it with you. So what I'm going to do is what I'm going to do here is I'm going to continue, start from the first one, right? And I'm going to add as many instructions as I can until I get to the structural hazard. And that would be my first convoy. So this is my first instruction. Okay. Can I go with multiply? Yes, because load is going to go to a separate unit. Multiply is going to go to a separate unit. That's also part. Third instruction is load. Now, since I have got single load, if I have this load also part of this convoy, that would be a structural hazard. So this means these 2 are only part of the first convoy. Then I start with the second convoy. So I've got load over here. Can I add this add instruction to the load one? Yes, I can, because load is going to go to the loads store unit, add is going to the add unit, right? Then I come across store. Can I add store to the load? No, I can't, because load store is a single unit. So this means this is going to be my second convoy. Then I have this third convoy. So these are 3 convoys, right? Load multiply is part of one convoy, load add is part of another convoy, and store is the third convoy, right? So how many chimes will this vector sequence take? It's just going to take 3 chimes, because there are 3 convoys, right? So if there are 3 convoys, it's going to take 3 chimes. Each chime is going to be a 64 clock cycles roughly. If you want to take it accurately, then you have to include the pipeline depths and the chaining cost as well, chaining time cost as well, right? Okay, the second question is how many clocks per how many cycles per floating point operations are needed, ignoring vector instruction issue overhead. Now, how many instructions per flops are needed? So this is the answer to the first one. Now the second is how many cycles per flop. Now how many floating point operations are there? How many floating point operations are there in this sequence? Now multiplication is a floating point operation and add is a floating point operation. Load, store are memory operations, right? So in total what we have are 128 operations, 64 operations here and 64 operations here, right? So 64 plus 64, 128 operations are
Excuse me, sir.
G.
Sir, add is a floating point operation because in add instruction we are adding V2 in the V3 and V2 is already having a floating point answer.
No. Add and multiply floating point operation because this is a multiply operation and this is an add operation, the arithmetic operations, right? Load is a vector operation, it's a memory operation, right? So there's a
Okay, sir.
difference between
Okay.
memory and ALU operations, right? So this is load and stores are memory operations, so they are not called as floating point operations. When you talk about floating point operation, when you're actually doing a floating point operation like floating point multiplication or floating point add or floating point divide or floating point subtract. So you're doing 64 floating point multiplications over here and 64 floating point adds over here. So in total you have got 128 floating point operations. And the question was, how many cycles are you going to take for these floating point operations? So the question was, how many cycles per flops are needed? Ignoring vector issue. So how many cycles per flop? So the question was, how many cycles are it's going to take to do these 128 floating point operations? So how many cycles per flop? So so there are 128 floating point operations and total cycles because there are 3 chimes. So every chime is going to take 64 cycles. So total number of cycles would be 3 into 64 for this whole thing to work roughly. So that would be 192 cycles, right? So how many flops per cycle? So you can just calculate that. So 192 cycles for 128 operation. That means one operation is taking about 1.5 cycle. Right? So 1.5 cycles per flop. So one floating point operation is roughly taking 1.5 cycle. So this is what we were supposed to answer over here. So 192 cycles since the sequence takes 3 chimes and there are 2 floating point operations per result. The number of cycles per flop is 1.5. So I hope you you are now familiar with a little bit of vector architecture and chimes and flow convoys. So in the next class, we are going to continue
Excuse me,
with
sir.
G.
Sir, can you please repeat the definition of convoy?
Convoy.
Yes, sir.
Okay. So when we were discussing about convoy, we said I'm going to come to that slide. Clear. Yeah, this was a slide when we discussed. So a set of vector instructions that can run concurrently is called a convoy. Now, when we're talking about convoys, we add instructions, vector instructions together, and we say that this is a set of instructions that can run together. Okay, so the instructions which are in the convoy must not contain any structural hazard. So this is the only thing that we have to look for, because if there is a structural hazard, then we cannot execute these 2 instructions together. What about instructions that are dependent on each other? They can still be part of the convoy, right? So if the instructions are dependent on each other, we said here that if there is a data dependency, the second has to wait till the first result is available. So once the result starts coming from the first instruction, then it can just forward that result to the second instruction, and that is called as chaining. That forwarding is called as chaining in terms of vector architecture. So these instructions can still be part of convoy. So in this example, we see an example over here in this case that multiply is using the result of load, but it's still part of the convoy. So for looking for the convoy, you just have to look for structural hazard. Now, if I change this question, and instead of single copy of each vector functional unit, if I say there are two copies of vector functional unit, that is, there are two load store units, two multiply units, two add units. And if I ask you again, how many convoys are going to be there? So what would be your answer? Again, the same thing. You start with the first instruction. This is there. This can be there because it's going to go to another unit. Can the second load be part of the first convoy now?
Yes, sir.
Yes, because there are two load store units. So this can be there because there won't be any structuralizer now. Add is going to go to the add functional unit. So this can be part of the first convoy. But now we come across store, because there are two load store. Third store instruction, because two already loads stores are busy. So the third one is going to create a structural hazard. So this is going to be our first convoy, and then this is going to be our second convoy, right? Because we have just
Okay,
got
sir.
5
Thank
instructions,
you so much.
right?
Okay.
Okay. So I'm going to stop over here. All of you were present today. I'm going to upload the slides. So our next class would be our last class, and up till now, Mondays are going to be our any updates? If there are going to be any updates, I'm going to tell that to you. I haven't received any formal instructions that exams would be on site or in university. But the plan is that master's exam would be conducted in the university. But at the last moment, it could happen that maybe there are changes, but up till now, the exams would be on campus, right? So you have to make arrangements for that. The first exam is on 12th October, and that's our exam, okay? So there is no gap. The next class would be our last class, and then you are going to have an exam on 12th October. So anything that has been covered after the 8th lecture, that is from 9th lecture to the 15th lecture, is going to be part of the midterm exam. Okay.
Okay, sir.
And sir,
Okay. Then.
and sir, what about the starting at lecture? Are those lectures not included?
No, those lectures would not be included.
Okay, sir. But sir, please try to use your source to extend the date of the exam.
Why? It's good that you complete your exam earlier, right? It's good that you complete your exam earlier, and then you can be free easily. Okay, so I'm going to stop over here. Okay, I'm going to stop over here.